Good morning to everyone who is able to attend my session. I appreciate your time and any feedback that you have at the end of this presentation that I have. My name is Anit Narendranath. I am a senior lecturer of mechanical engineering at Michigan Technological University. And for this particular presentation, I am demonstrating a few learning analytics tools that I've created using the Wolfram language in the Wolfram Mathematica notebook environment, obviously, which plug and play into a couple of courses that I teach, but certainly have the potential to evolve and scale beyond just my few courses. Those of you who are present, particularly if you are instructors or teachers, there is a survey of 2 questions that I have embedded in your Pathable chat window in the poll section. I request that you take that survey so that I get a feel of who the audience here is, so that I can have a bit more of a targeted approach to a few of the slides that I have. So in the Pathable window that I'm thinking you're watching this presentation via, you have a couple of tabs: chat, polls, files, and people. Under the polls section, you should have 2 questions that I request that you answer. The first question is, as a teacher, what is the structure of your examinations? When you create examinations, do you create examinations with problems of mixed complexity and structure, or do you create examinations where problems have incremental difficulty or complexity and structure? The second question is, how do you assess and evaluate your examinations for your students? Is there some partial credit available for your examinations, or is it an all or nothing deal with no partial credit? These are some of the supports, if you will, mathematical supports for what I am about to discuss. So I'll give you maybe another 30-40 seconds to take a crack at these surveys, and you can feel free to continue doing that through the rest of the session. So as you do that, I'd also like to take a minute to touch upon the point that the future of education will contain in it learning analytics. Now, this learning analytics, you could think of that as a suite of digital tools. In this case, these were created using the Wolfram language, which could potentially source data from education big data, so to speak, that is generated by individual students, by classrooms, by universities on a very regular basis. And by sourcing this data, you could have actionable intelligence that you as an instructor or some other decision support system would act on it to provide feedback or interventions to individual students for full classrooms. Maybe you could use learning analytics tools to enhance or improve your curriculum or the way you create examinations, and so forth. So when I look at the survey, so far not too many people have answered it, but that's fine. Most people say that when they create examinations, they do so where they have problems of incrementally increasing complexity. And when they assess and evaluate their examinations, there is some partial credit available. There isn't a correct answer to this, obviously. It's not that some of us are correct and some of us are wrong. So what I will describe as part of this presentation are 4 pieces. One is an exam forecast Monte Carlo sampling type model for an entire class. The second is a time on task visualization to identify common failure modes suffered or experienced by students in a classroom in this particular course that I'm using these for. A K-means clustering, I think, module for the recognition of improperly categorized grades. And finally, something that is still a work in progress, a Markov model to evaluate time to mastering certain content. Right. So those are the 4 pieces I will look at. Most of my time will be spent on the exam forecast model that I have created. So you could think about this as a current story or a pain point, and which I've depicted using graphics over here. What you have here is students studying for their tests or doing their homework assignments and so on, and then going into their assessment, which is their examinations, and eventually they have grades at the end of the assessment. But the grades themselves do not actually provide much along the lines of continuous improvement, because letter grades may not always be representative of mastery. That's one of the key pain points. They have arbitrary granularity. Letter grades are pretty much a line drawn in the sand. and they do not provide adequate feedback to students or may not provide adequate actionable intelligence to instructors. This is particularly true for large class sections. This argument may not have much weight if you have a very small class section, 5 or 6 students, because then it's a pretty intimate environment in that case. But if you teach class sections such as what I have with hundreds of students, it's not, just using this approach is not the best method, particularly if you want to introduce some sort of a feedback loop for students or to provide them with intelligence towards continuous improvement. So that's the current story or pain point that I suffer, certainly. So the desired story or the resolution of this pain point is that the first couple of pieces pretty much stay the same. The instructional aspect of things and the assessment creature, which is your examinations, may stay the same, but instead of letter grades, you would actually present to students some sort of a multi-paradigm dashboard, almost like a multi-paradigm data science thing that Mathematica is pretty good, the Wolfram language is pretty good at, which would also indicate to students the various pathways of continuous improvement. Right, so student performance on examination specifically should actually result in multi-paradigm data. It shouldn't just be a letter grade. But for this to actually happen, it is necessary to pipeline all or as many different pieces of assessment and performance data to create a more rounded or coherent picture of progress. So that's the desired story, and the learning analytics tools that I present are seeds that would probably grow into some sort of a multi-paradigm dashboard. So what are the research questions or the questions that I'm trying to answer? There are lots of branches and ramifications here. Mainly the blue thing is, can student performance be deconstructed into many components? I think it can, provided you create examinations in a certain fashion. The other questions, the sub-questions of that, sub-parts of this question is, can exam performance be estimated or forecast? I think you can. But how do we do it? Can we have a simple parametric model to forecast examination performance? I say, yes, you can. Can examination performance uncover discrete mastery levels? Possibly. Can clustering, K-means clustering and so on, replace or support the traditional approach of assigning letter grades that a lot of us do? I'm not saying everyone does that, but that's generally the context of assessment in post-secondary education, STEM education specifically. And what about time on task? A time on task in the context of an examination is how much time does a student spend on a particular exam question. Can the time on task data, when accumulated for an entire class section, can it uncover any universally experienced challenges? And if you can couple that with all the other pieces that I'm trying to answer, would that provide a semblance of a feedback loop for students? So those are some of the questions I'm trying to answer. A lot of stuff to digest. Learning analytics is still in somewhat of its infancy, but there is a lot of data science involved here and pipelines, which I'm thinking many of us who use the Wolfram language recognize and understand. Now let's talk briefly about examination design, because in the following slides, you will see that I speak of something called traditional examinations and hierarchical examinations. An examination or assessment pieces can be designed via this kind of a map. You could have problems on an examination chosen from any of these 4 quadrants. For the traditional examinations are generally just pick problems from a textbook, put them in your examination, and let students have at it. A hierarchical examination, the way I define it for the purpose of this presentation, is you choose problems of incremental difficulty which fall on this map somewhat. The course that I am focused on is strength of materials or mechanics of materials. It's a second-year course for mechanical engineering students, and examinations are mostly designed in the second and third quadrant, from the second and third quadrant of this map, where you have generally well-structured problems, which range from low complexity to high complexity. You don't really have ill-structured problems in this particular course. It's generally first you do this, next you do this, then you do another thing, and voila, that's your answer. Right, so that's where examinations are in the context of this presentation for this particular course. So let's take a look at what I used to have as far as student performance on examinations, for traditional examinations, where I would just pull problems from a textbook without really paying too much attention to the difficulty levels and where they are on that examination map. And you see some kind of a graph, which most of us would say, okay, you have a normal distribution of student performance and so on. That's what we had for traditional examinations that I conducted about 2 years ago. I moved on or modified my approach to having a hierarchical examination. And when I did that, I noticed that there was a difference in the student performance. One of the clear things that's pretty clear here is that a greater number of students achieved 100% on examinations that were hierarchical, where achievement of each level is built on the level before that. Also understand that in this case, to prepare students for such assessment, instruction is also hierarchical, the way you progress with it. So that's a bit of a difference. So I thought, yeah, that's pretty interesting. So what I look at next is instead of looking at histograms, why not look at KDEs, kernel density estimates, distribution estimates, what have you, because these represent characteristic curves of student performance from a more probabilistic standpoint. Examination performance is pretty probabilistic. One may even go as far as to say that you'd need to have Bayesian forecast models to forecast the performance of students on examinations and so on and forth. So I have two different characteristic curves. The green curves are for the traditional examinations that I had, while the blue characteristic curves are for the hierarchical examinations. And these are important. These curves they are curves, they're not bar graphs with these discrete, this discrete nature. They're far more fluid in nature, they're far more smooth. So, okay, so we've recognized that there is such a way of creating hierarchical examinations, as I call it, and there seems to be or appears to be a difference in student performance on traditional examinations versus hierarchical examinations. The point here is not that, oh, students will perform better on hierarchical examinations, but the point is that there is a difference in performance. And the number of students I think that I had in this, I would like to say, is anywhere between 100 to 150, I would like to think. So that's a pretty large classroom. Okay, so the other thing, one of the research questions I had was, what about, can you identify discrete mastery levels? Now, it just so happens that when you look at, when you construct a hierarchical examination, the scores that students achieve represent their mastery level on that concept. Their scores are the discrete mastery levels for a very large extent. And hierarchical examinations generally have fewer mastery levels because you have 5, 6, 7 questions, whatever, and you have those as your mastery levels, versus a traditional examination, which is far more organic, and you can't really decompose a traditional examination very easily into mastery levels. So the other one question that I think I have answered, maybe the jury is out on it, but I think I have answered, is that hierarchical examinations do possess the property that the scores identify are a signature of mastery on some concept, and you have fewer discrete scores. This is a good thing because you can, this helps you diagnose and identify any conceptual deficiencies or exam design deficiencies for that matter, with some of the other learning analytics tools I have going on. Okay, so the first tool that I have after that preface is forecasting the performance of an entire class section, right? So I have several semesters of examinations that I have a smooth kernel distribution, a KDE of sorts, and I have a Monte Carlo forecast model that generates a family of curves given a certain difficulty level on an examination. This family of curves is the probability density function, or the KDE function family of curves, which could be the forecast outcome of an examination. These are the various outcomes that are possible. Now, the key point here is that we have a parameter which is called examination difficulty, which I have not yet resolved. What exactly does examination difficulty rely on? I don't know. But for now, it varies between 0 as being it is not a difficult examination at all, everyone should receive 100 points, to 1.0, which is a particularly difficult examination. And I think in this particular scenario, that you will see next, I fit my KDE for a particular examination, or rather I superpose my KDE for a particular examination performance of my students on the outcome of my forecast model. And I see that examination one doesn't quite line up with what I had in my Monte Carlo forecast model. So maybe my forecast model was not that great, is what I initially thought. I proceeded further to probe that by saying, okay, let's, I have my forecast model with examination difficulty of 0.3. And well, it so happens that a portion of my code is crashing the notebook, as it is bound to happen during live presentations. That's pretty unfortunate. So I will have to skip that portion and move on to the next thing, which is a time on task. Now, what exactly a time on task is how much time a particular student spends on a problem on the examination. And it just so happens that when you create a traditional examination, time on task kind of looks like this. On problem one, a student spends 5 units of time. On problem two, the student spends 2 units of time, 5 units, 4 units, 6 units, and so on. That's what a traditional exam looked like. Now, when I went to a hierarchical examination, what you would think is, you would have a step-like creature for your time on task because you have incremental difficulties of content. But so happens that when you gather this time on task information, which is possible if you conduct examinations through learning management systems and you have learning management logs, I find that when I look at the time on task for all my students in a particular class, this is what it looks like. For some of the earlier problems, there is lesser time being consumed, and later problems consume a larger amount of time, which kind of makes sense because the examinations get incrementally more difficult. Kind of makes sense. So we'll take a look at one other examination. Similar kind of dynamics. It kind of goes up. It would seem that in this particular time on task, students spent quite a lot of time reading the instructions for some reason. And the last question is a file upload question. Their written work has to be uploaded. But what was interesting was one of the examination completely went against the grain, where the time on task had somewhat of a descending steps later on in the examination, with one problem taking about I think 45 to 65% of the time consistently for all students, which is supposed to be of lesser difficulty than an immediately next problem. That was very strange. That was a very curious incident that made me probe that particular examination. And I found through the time on task metric that that particular question on an examination assumed a prerequisite that students did not quite have. That was not actually apparent to us or obvious to us in our curriculum, but that was something that we uncovered as through this time on task metric, that, oh, this question, that this particular question's mastery that we are looking at or assessing students on, they don't have the prerequisites for that, and hence they struggle to do certain mechanical things for that particular problem. So that was a pretty interesting outcome that we had from the time on task metric over here. And finally, in this case, I look at k-means clustering of grades. Now, this is something which this is a pet peeve of mine. We use these letter grades, which are essentially lines that we draw in the sand and say, oh, you have 92%, so you get an A. You have 91%, so you get an AB. That's a line in the sand. So what we did is, instead of using the traditional technique where we have students turn in homework assignments, examinations, and do weighted averages and say, okay, if the weighted average is above a certain cutoff, you get such a letter grade and so on. We retained that information, but we also divided the students' work into 3 or 4 categories, which were based more on certain barriers that they would have in those categories. Individual work has different cognitive barriers or learning barriers than does group work. And timed examinations have different barriers and stresses and pressures as compared to individual and group work. So we distributed students' work into different categories based on the barriers, presumed barriers. We applied, I think in this case, a principal component analysis to reduce the dimensionality, since we had a multidimensional data table. And we used a k-means clustering algorithm that we have access to via Mathematica to compare the traditional grading scheme, which is weighted averages, where you have 3 students receiving an A grade, then you have an AB grade in yellow and green and so on. And we compared that, the traditional technique of weighted averages, with what was I saying? I completely lost my train of thought here. With k-means clustering. And we found that when we use a k-means clustering instead of traditional weighted averages, we find a misrepresentation or a miscategorization of some students who should have been in the C grade category but received a failing grade. That sent a few alarms that made us think about it a little more, that obviously, letter grades are a line in the sand, which are not really good. Perhaps we need to support such a grading scheme with a machine learning construct such as unsupervised clustering in this case. So that's another piece of the learning analytics toolbox that I had designed. And it works for my course, but it has the potential to evolve and scale for a curriculum. Finally, what I'm looking at is a Markov model, because on an examination, students go from one mastery discrete level to another mastery discrete level. The initial forecast model that I have, if I run it for say a couple of thousand times, and it's actually a pretty good forecast model. Too bad I wasn't able to demonstrate that because of the way it interacted with my Mathematica presentation environment. But if I run that Monte Carlo scheme for a couple of thousand times, I'm able to generate a transition matrix, a Markov model transition matrix, which defines the probabilities of a student moving on from one mastery level to another mastery level successfully. And that is where our research is right now. If we were to define a transition matrix of success for students moving from one mastery level to another mastery level, can we determine how many attempts it would take for the entire class to have mastered a certain content? Yeah, oh well, a lot of things breaking down here, but that is what the Markov model scenario we have here is. At this point, I'll stop my presentation because a lot of things are falling apart in my document, which didn't just 30 minutes ago. And I would be very happy to answer any questions that you may have. Well, if there are no questions, oh, there is something here. My notebook is available to download, though. There is that thing. If you wish to work through the functions in the notebook, the data has been embedded in GitHub. So that should be accessible to everyone. So you're more than welcome to download my notebook and work through it if you wish. And that should be available in the Files tab of the Pathable window, Pathable page for this particular presentation. How many thousand hours of work do you think it would take to fix Mathematica? Honestly, I wouldn't blame Mathematica alone for it. No. A lot of nice analysis methods. Thank you. So I'll underscore that there were 4 things in my toolbox. One was a forecast model, a Monte Carlo forecast model that actually quite effectively forecasts the performance of an entire class on an examination. The second one was a time on task visualization that allows you to triangulate if there was any particular problem on an assessment piece, such as an examination, that troubled students a lot. And it just turns out that this allowed us to identify a certain lack of prerequisite knowledge. The third one was using k-means clustering techniques as a support to traditional letter grade assignment. I think there is a lot of merit to it. Weighted averages are a single point indicator of not much sometimes. And finally, what I'm working on currently is a Markov model with a transition matrix created using my forecast model that would give me an indication of how many attempts would an entire class need on an assessment piece, such as an examination, to master all the content 100%. As a metric for analyzing, I have a question here. As a metric for analyzing student comprehension, is targeting some specific grading distribution the right way to go? I don't think so. One of the things that happens in higher education is that we have a presupposition that student performance is normally distributed. That's not necessarily true, and that is significantly a function of how you design an examination and what your assessment scheme itself looks like and where those lines in the sand are drawn. So it's not. How best to apply these techniques to small classes? These techniques can, they can be used without any modification to my notebook for small classes. Besides that, if there's something specific that you'd like me to touch upon, I'd be happy to do that. I would, at my university, this is being used at my course, in my course only, because we do not have a very strong thrust towards learning analytics at this stage. Data collection is a key feature. That's actually a pretty, it's another question over here. Is data collection a key feature? It is important. I would say that a lot of learning management systems that I have used are hamstrung by the fact that they don't allow a lot of data, clickstream data, besides gradebooks. So that's the thing. So one way out of it, and I was hoping that there'd be a presentation on that, and I think it got canceled, was creating your own learning management system that allows all this data to be collected, which brings into question another aspect, which is consent. I mean, if you're actually collecting all the student clickstream data, they should have consented for that particular data to be used for learning analytics. But that's yeah. Well, if there are no other questions, I will certainly end this session.